Good morning, everyone. And this is my name is Taylor Gup. It's AMA 325, Electrical Fundamentals Theory DC3. Let's get straight into this. No, not right. Well, put your back again. No. But overnight, guys, we'll get straight into this. Today's topic, we're going to be talking about the DC generator. To start off with, what is a DC generator? A DC generator is a rotating machine that supplies electrical output with unidirectional voltage and current. The field is produced by direct current in field coils or by permanent magnets on the stator. The output or armature windings are placed in slots in a cylindrical iron rotor. These generators are used to charge batteries, provide lighting, and provide excitation to the alternators. They are used to provide field excitation current for regenerative braking in DC locomotives. They are used in DC motors where speed control is necessary. So the difference between an AC generator and a DC generator in short form, an AC generator creates an alternating current that periodically reverses direction. But in a DC generator, a direct current flows in one direction. Our lecturer Master Vinit has given us an assignment to build a model of a DC generator and 5 questions related to general information of how a DC generator works. Alright guys, so this is the model that I've made. It's simple materials used at home just to show the interior design of a DC generator. In this model it consists of an armature or armature coil, the commutator, the 2 brushes on the sides, the external circuit where the direction of current flows. This represents the permanent magnets, north and south pole, and this line in between represents the magnetic force between the permanent magnets. So in a diagram it should look like this. So without any further ado, let's get straight into the questions. Question number 1 is to make a model and explain the constructions of it. So in this simple DC generator model, it consists of 3 main parts, which includes the magnetic field systems provided by the north and south pole, also known as our permanent magnets, the armature, and the commutator with the brushes gears on the side. If we take a look at the diagram, there are other parts of a DC generator, which are the magnetic frame, the yoke, pole core, pole shoes, field coils, armature core, and windings, together with housings, bearings, and shafts. The 2 essential parts of a DC generator is a rotor and a stator. In this stator has a main function to provide magnetic fields where the coil spins, and the rotor has a main function to decrease the loss of eddy currents. The next part is a yoke, main function to give necessary mechanical power for carrying the magnetic flux through the poles. We also have the poles, mainly used to hold field windings. Pole shoes, mainly utilized for spreading the magnetic flux and avoid the field coil falling. With the commutator, the main function is to convert AC voltage to DC voltage. We also have the brushes. The electrical connection can be ensured between the commutator as well as the exterior load circuit with the help of brushes. Question number 2. Explain the working principle of a DC generator. So if we take a look at the diagram again, a DC generator operates on the principle of Faraday's laws of electromagnetic induction. According to the Faraday's laws, whenever a conductor is placed in a fluctuating magnetic field, or when a conductor is moved in a magnetic field, an EMF is induced in the conductor. If the conductor is guided with a closed path, the current will get induced. The direction of the induced current, given by the Fleming's right-hand rule, changes as the direction of movement of the conductor changes. So, just using the little piece of the armature with the conductor. So consider the case as an armature rotated in a clockwise direction and the conductor left moving in an upward direction. As the armature completes its half rotation, the direction of the movement of the conductor will get reversed downwards. So the direction of the current will be alternating due to the magnetic forces from the permanent magnets. As the connection of the conductors will get reversed, a current reversal takes place Thus, we get unidirectional current at the terminals. Question number 3. What are the common faults of a DC generator? We got 1. Sparking off brushes. Some sparking at brushes is normal. Excessive sparking may be due to worn brushes, resulting in reduced spring pressure, or due to roughness of a commutator segments. Number 2. Failure of excite. Some reasons of failure of excite of a DC generator is the absence of residual magnetism, wrong field winding connection, wrong direction of rotation, resistance of field winding, or speed of rotation. Number 3. Overheating of a DC generator. There are typically 5 main reasons of overheating, which is overload, poor power condition, high effective service factor, frequent stops and starts, and environmental reasons. Question number 4. What are the losses that occur in a DC generator? Number 1, we got copper loss. These losses occur while current flows through windings and are of 3 types: amateur copper loss, field copper winding loss, and losses because of brushes resistance. Number 2, we got iron losses. Due to induction of current in amateur, eddy current losses and hysteresis loss occur. These losses are called core losses and magnetic losses. And number 3, mechanical losses. Losses which occur because of friction between the parts of a generator are called mechanical losses. Question number 5. List the methods of cooling systems in the DC generator and explain why. Before we get straight into the real explanation, why do we need to cool down generators? Most generators have numerous conductors, which all produce heat as current flows through them. That heat can build up quickly within the system, and it must be properly removed to reduce the risk of damage. There are 2 cooling systems in a generator. We got the air cooling system and a liquid cooling system. The first is open ventilated systems. Here, the air in the atmosphere is used with a type of exhaust system. This allows for the air to be released right back into the atmosphere. It pulls the air and pushes it back out into the surrounding area. The second type is an enclosed system. An enclosed system, as the name implies, keeps the air in place. It works to recirculate the air. As it does, the air is cooled, which, in turn, keeps the generator cool. Air-cooled systems have some limits, including the risk of overheating. However, air-cooled systems are mostly restricted to small standby and portable generators that produce up to 22 kilowatts of power per unit. Next, we have the liquid-cooled systems. Liquid-cooled systems, sometimes referred as water-cooled systems, are another option. A liquid-cooled system features a water pump that moves the coolant around the engine using a number of hoses. The heat from the generator transfers naturally to the coolant, cooling the unit. This type of system is best for large generators in particular. They require more heavy-duty components to keep the generator cool. One key option is the hydrogen cooled system. They are also used for large generators. The hydrogen used in them has a high thermal conductivity. This allows the systems to pull out the heat at a faster rate. As a result, they work well for large systems that cannot be efficiently cooled using other coolants.